Hey guys, I'm back. So this is lesson 2 for phases of matter, and we're just going to talk about solids and liquids today, and we're going to also identify the 3 major phases of matter and the properties of matter at those specific phases, and we will illustrate those phases using what are called particle diagrams, which we will just draw a few particles to indicate what a solid, liquid, or phase would actually, or solid, liquid, or gas phase would look like. Alright, so let's start with phases of matter, and you can check out this link on my school webpage, okay, through Schoology. Apparently it's not working, so just try to click on that link through my school webpage there. Matter exists in 3 forms at STP, standard temperature and pressure, and this is on table A in your reference tables. The first one is solid, and that is indicated by a little s in parentheses. Liquid, the second phase. The third one is going to be gases, and indicated by the little g. Look at this symbol here. It kind of looks like a C, but it's a little L, okay, a cursive L. The fourth one is plasma. As you all know, that is the 4th phase, but that is considered an ionized gas, and we're not concerned with this phase in chemistry, so we're just going to stick with solid, liquid, and gases. And aqueous is not a phase, okay, but it is a state. So this is where a solid is dissolved in water and becomes a solution, and you would see the symbol AQ in parentheses after the substance. Okay, so when we look at this little picture here, this diagram, we see solids. The particles are tightly compacted, and when they melt, they become a little more spread out into a liquid, and then they vaporize, okay, or evaporate into a gas, and the particles are all over the place, random motions. Okay, and then let's look at our properties. Now you have this table in your notes. You need to study this table. So we need to know the properties of every single phase. Okay, so we have solids with a definite shape, liquids takes the shape of the container, and gases also take the shape of the container. Volume for solids is definite. Liquids, it's also definite, but gas will take the volume of the container. So if you were talking about air in a room, okay, the volume would be based on the size of the room. Okay, particle movement for solids vibrates about a fixed point. Okay, so there is particle movement in a solid, even though it appears that it's not moving. Okay, there is a tiny amount of vibration within those particles because there's still a little bit of energy. Okay, at the freezing point, and when it is completely a solid, there's still a little bit of heat left in there. Okay, it's not absolute zero. Vibrates about moving points for liquids, okay, so it flows, and then in gases, free to move all over the place. Most freedom for gases, for the particles. Density is going to be very high for solids because it's very compact. Also still going to be high for liquids, and then very low for gases because you have large distance between particles. So density is going to be based on the distance between particles, and it's different between solids and liquids. Okay, if you look at the particle diagrams in the last part of your table, you will see they're still compact, but there's ability to flow for a liquid. And then intermolecular forces, if we go back to the bonding unit, when we talked about that, it's the forces between the molecules that kind of keep them together. It's like Velcro, okay? It's not a bond, but it's just a force, sorry about that, that keeps them together, okay, or the attraction between the particles. So at room temperature, solids are really strong. Liquids still kind of strong, okay, but then they get weaker. Those forces get weaker as we go to the gas phase, and those molecules fly, roam freely all over the place at room temperature. The particle diagrams are indicated here. So when you are presented with a question on the Regents about the particle diagrams, and they want you to draw a few particles to indicate the phase of a substance, you would draw it out simply like this. Okay, for a solid, very tightly compacted. For a liquid, you can kind of separate them a little bit, but just show that they're kind of on top of each other, but it allows for movement, flowing. And then for gases, should be random all over the place in your little particle diagram box. Okay, so let's go to solids and liquids, and we have this diagram here, it's called a heating curve, okay, and this indicates to us the relationship between temperature and time and how the phases change over time and when heat is added. So, and that's over time. So as heat is added, the substance changes phases. So at point A, it's all solid. Point B to up to C, we should say, is a solid and a liquid. Now notice how it's flat. Temperature remains constant there. Okay, so potential energy is actually increasing where it's flat. Okay, increasing at, let's say, plateaus. Okay, and our kinetic energy, where the molecules and the particles are moving, okay, and getting enough energy to move around, are going to be on the inclines. Okay, so this is where kinetic energy, and I'm going to abbreviate those, kinetic energy is increasing here, okay, and also here at E, and also down here at A. Okay, so that's when a solid, when we heat it up, the particles are gaining enough energy to move and then break apart to become a liquid. So when it starts to melt, it's actually in two phases. So an ice cube is actually liquid and solid, okay, because it's at that melting point, the freezing point, which is at 0. Now, when it starts to melt, again, at 0 degrees, so the melting and the freezing point are at the same temperature, which is a little confusing, but if you think about it, that's exactly at the same point, the temperature 0 degrees Celsius, when a solid does start to become a liquid, and also when a liquid will start to become a solid. So that's why we have two phases there. Okay, at C, now it's going to be all liquid, and then once it starts to hit the melting point, okay, so this would be, I'm sorry, not your melting point, your evaporation point. Okay, so where I circled, okay, that's going to be your boiling point, okay, and when the liquid starts to turn into a gas. So I'm going to change my color here. So this is going to be your boiling point right here at this point, and then here, right there at that little peak, okay, where it starts to change is your melting point and your freezing point. That's 0 degrees, okay, 0 degrees Celsius, so ... 0. And then up here, if we come across, we're going to say that's 100 degrees Celsius. Okay, we're going to practice drawing these out and looking at them. There's a lot of information that can be gained from this diagram. Okay, at point E, you have an all gas phase. Okay, so liquid gas, as soon as it hits boiling point, it starts to, you still have liquid, okay, and then it starts to vaporize, okay, and then you have your vapor or your gas. So you have two phases at that point. When it is completely finished, okay, and that's at your plateau, potential energy is increasing, it's storing up, and then finally, when all the liquid is gone, you have all gas. And then the temperature starts to increase at that point. Okay, so the liquid is the phase of matter characterized by its constituent particles appearing to vibrate about moving particles, or points. I'm sorry, evaporation is the process by which subsurface particles of liquids escape into the vapor state. So this is a phase change from liquid. The question says, can a liquid evaporate if its temperature is below its normal boiling point? The answer is actually yes, it can. Okay, and this is because if we look at that phase diagram, and I'm going to scroll up a little bit to the previous page, all right, if we look, what's happening here, this is a liquid and a gas. So here's your boiling point. It actually starts to turn to a gas right here. So evaporation can actually start to occur below the boiling point as long as you have enough kinetic energy. Okay, so yes, it can with enough kinetic energy, and this is when this is evaporation, or when evaporation begins to occur. So you have two phases going on, liquid and a gas. Okay, vapor pressure, table H. All right, so if you look at table H, and I don't know if you can see this, all right, in your reference tables, okay, has these curves here, gives you an idea of vapor pressure for specific substances that we are going to be talking about later. But what is vapor pressure? It's the upward pressure exerted by a vapor in equilibrium with its liquid. So it's going to keep it a liquid until some force is exerted on that, okay? So it's a balance. So what happens if the vapor pressure of a liquid is equal to the atmospheric pressure? What's going to happen is that atmospheric pressure now pushes down and becomes the same as the vapor pressure and puts that force on the liquid and causes it to boil, okay? So that's what happens. What happens? The liquid starts to boil. All right, so now talking about solids, the phase of matter characterized by particles that appear to vibrate at about fixed points, very slight vibration. So let's read these points here. As the temperature of a liquid is lowered, the forces of attraction become stronger, so those particles become tightly compacted. The attractive forces arrange particles in a very orderly fashion, nice and arranged like a crystalline structure or a lattice. The motion of the particles becomes severely restricted and they vibrate in place. Okay, the temperature at which a substance becomes a solid is called its melting point or freezing point. They are the same exact point. Okay, so don't get those mixed up. All right, a substance melts and freezes at the same exact point, 0 degrees Celsius. So all true solids have a structure called a crystal lattice. That is what is the orderly fashion, like I stated before. And these links are on my school website, so I'd like you to just check out the crystal lattice of graphite and diamond and compare the two. For additional homework, what I'd like you to do is answer the questions 1 through 7 at the bottom of page 10 here. Okay, so I'm going to go to that page right here, these sets of the set of questions here, and I will check it and I will grade it. So